All right, so this is Wisconsin Engineering 19, hydraulic formulas for orifices, weirs, pipes, and chutes. Mike, can you just confirm they can see and hear me?
I can see and hear you, and the recording has started.
All right, thank you. All right, so today we're going to be talking about drop inlet structures. Those are kind of interesting structures. They deal with pipe flow, orifice flow, and weir flow. And so there'll be a combination of all three of those. So we're going to kind of start off here talking about the different types. So the pipe, the weir, and the orifice. We'll break those down individually. And then at the end, I'll kind of bring it all together and we'll talk about drop inlet structures. You're going to want a paper, a pencil, and a calculator for this. There'll be times throughout. We're going to work on some examples. Anybody who would like a PDH credit for it, please email me and I'll get those sent out to you. For folks in the NRCS, this class is registered in AgLearn, so if you want credit for that, feel free to register in AgLearn. All right, we're going to kind of start off talking here about orifice flow. So an orifice is defined as a hole of regular form through which water flows under pressure. Orifices may be circular, square, rectangular, or any other regular shape. And then in a case of a circularizer, the orifice flow cannot occur at the crest of the inlet until H is greater than half the diameter of the riser. So what that means is if I have a 30-inch riser over here and then my water's above it, it has to be a minimum of 15 inches or half of this diameter above it to be an orifice flow. So if this was 48 inches, this would have to be 24 inches. If it's below that, it's going to be considered weir flow. So free discharge occurs when the water is discharging through the orifice into the air. In this case, I have a body of water here. It's discharging through my orifice, and it's free discharging there. There's nothing restricting it. A submerged discharge occurs when the water is discharging through the orifice into water. So here I have my body of water. It would discharge through my orifice into another body of water, so that water is going to restrict it. When we're talking about head in these, the head will be actually measured from the two water surface elevations. We'll talk about head a little bit more here on the next slide. So here's our basic orifice flow equation. Q is going to be your discharge in CFS. C is going to be your orifice coefficient. So for our soil conservation work, we're always going to use 0.6. A is going to be our flow area or area of our orifice. G is going to be our acceleration of gravity. So this is always going to be 32.2. And then H is going to be head, which is measured from the center of orifice and free discharge. So if we kind of look up here at my photo, here's our orifice. What we're going to do is we're going to kind of find the center of it or the midpoint of it, and we'll measure up to the water surface, and that's what's going to be your head. If we were in a submerged flow, so if my water surface was up here again, it would be the difference between the two water surface elevations. So here's kind of an example. I'm going to just go through this first one, and then I'm going to have a couple for you guys to work on. This first one is I have an orifice that's 18 inches by 18 inches. My flow line is, yep.
Kyle, you're speaking a little too fast on your slides.
Okay.
So let your slides come forward and then speak, because we're not seeing what you're pointing at.
Okay.
All right, thanks.
Yep. So hopefully you can see this then. So okay, on my example here, I have an orifice that's 18 inches by 18 inches. And then the bottom here elevation is going to be at elevation 100. My weir coefficient is going to be 0.6. And then I'm going to solve it for when my surface water is at 106 and 110. So the first thing I'm going to try to figure out is where the center of my orifice is at. So again, I know that the bottom here is at 100, and then that my opening is 1.5 feet or 18 inches. So I'm going to take half of that to get to 0.75 to find my center. So I'm going to take 100 plus 0.75 to get to 100.75. And then I know that my height of my water is at 106. So I'm going to take that, subtract out my center of orifice, which is 107.75, to get to 5.25. My area is going to be 18 inches by 18 inches. I'm going to divide that out by 144 to get to 2.25. And then here's my general equation again. I have all my unknowns, so I'm just going to plug those in. And I'm going to come up with 24.8 CFS. So on the next one here, again, my center of orifice is going to be at the same elevation. So I go through the same process of 100 plus that 0.75 to get to my center. This time my water surface is going to be at 110. So I'm going to take that, minus out my center of my orifice at that 100.75. So I'm going to have a head of 9.25 feet. My area again is going to be the same, that 18 by 18, divide out by 144 to get to 2.25. My general equation again, I'm going to plug in all my unknowns, and I'm going to come up with 32.9 CFS. So notice the thing to point out here is as my head went up, so did my flow. All right, so I'm going to have you guys kind of work through this one a little bit. It's kind of the same process I just went through. The only difference on this one is that my width is going to be 18 inches on this one, and my height's going to be 12 inches. Again, this elevation right here is going to be at elevation 100. My weir coefficient is still going to be 0.6. And then again, we're going to solve for water surface elevations of 106 and 110. And then here's the equation so you guys can follow along. When you guys are kind of getting done with those, please put your answers in the chat, and I'll kind of know to move on and talk about this a little bit.
What is the G variable?
That is gravity, so it's a constant, so it'll be 32.2.
Oh yeah, thanks. Are we supposed to add the 0.6 coefficient to elevation or something? Was that part of your process?
So the 0.6 will just be C, and then you got to figure out where your center of your orifice is, and then subtract that out for your head.
Okay.
So you have to add that 12 or half that 12 inches to the bottom, which is at elevation 100.
Kyle, we have a question whether the slides will be available.
Yeah, I will make them available, whether we put them on our SharePoint or if you just want to email me and I can get it to you.
Okay. We at the end of the presentation, if you put it in the chat, then people could actually download them as well.
Okay, yeah, I think I'll do that way then.
Okay. And Kyle, afterwards, this calculation, could you go over what the difference between a weir and an orifice is?
We'll kind of
Again.
hit the weirs in a little bit later here. So
Okay.
I'll get to that.
Okay, very good.
All right, I'm going to start kind of going through these a little bit here. All right, so for this first one, the first thing we're going to kind of figure out here is we got to figure out what the center of our orifice is. So again, we had this elevation here on the bottom of our orifice was at elevation 100. And we knew that the height of this was 1 foot. So to find the center of it, I got to kind of take the midpoint of those two. So I'm going to take that 1 foot divided by 2 to get to this 0.5 feet. So I'm just going to take my 100 here plus my 0.5 to get to 100.5 feet. And so that's going to give me the center of my orifice. And then we were given that our water surface elevation up here was at 106. So I took my 106 minus my 100.5 to find out that my head is 5.5 feet. And then I'm going to kind of calculate out my area, which is going to be this 18 by this 12. And that's going to get me to inches squared. So I had to divide it out by 144 to get to feet squared. And so I come up with 1.5 feet squared. Okay, so here's my general formula. I was given C of 0.6. A I calculated at 1.5. G is given is a 32.2. And then H is 5.5. So I calculate those out. I get to 16.9 CFS. All right, so for when the water elevation changes, again, I'm going to have to find the center of my orifice first. So I'm going to take this 100 again, and I'm going to add up the midpoint, which is going to be 1/2 foot to get to 100.5. My water surface is going to be at 110. So I'm going to take the difference between the center and my water surface and come up with 9.5 feet. Again, I'm going to take my height times my width of 18 times 12. That's going to get me in inches squared. So I have to divide it out by 144 to get to feet squared. And then again, my general formula, C is given again, A is 1.5, G is 32.2, and then we found out that H is 9.5. So I plug that into my equation and I come up with 22.3. So kind of the things to note on this again are as my head increased, so did my flow. But from the examples that I did to the examples that the second set is the orifice size decreased, and as my orifice size decreased, so did my flow as well. Okay, so here's kind of another example. This is one when the orifice is on a horizontal plane. And I'm just going to kind of run through this one. So I have a 2-inch orifice. It's sitting down here. And then I have this elevation here is at 100. And I'm going to solve it for when the water surface elevation is at 102 and 101. And so I know that my orifice is going to be down here at 99 because I'm going to take this distance, and it's 1 foot. So my orifice is sitting at elevation 99. So kind of going through these. So my water surface elevation is 102. And again, I knew that my orifice is sitting at 99. So I'm going to take 102 minus 99 to get to my head of 3 feet. And then I'm going to do my area formula, which is going to be pi d over 4. And d is going to be squared. And then this divided by 12 is to get me from inches to feet. So I multiply that through and I come up with 0.0218 feet squared. Here's my general formula again. C was given, A we just calculated, G is 32.2, and then H we calculated at 3 feet. So I plug those into my equation, and I come up with 0.18 CFS. All right. So now for when my water surface elevation is at 100.1. My head, again, my orifice is going to be at 99, so my head's going to be 101 minus 99 to get me down to 2 feet. Again, I'm going to calculate my area through, and I'm going to come up with the same results as I did on the last time. And so I'm going to plug these in. I know this is 0.6. My area just calculated. G is always 32.2, and then H is 2 feet. So I plug those in, and I come up with 0.15 CFS. So again, as my head goes down, so does my flow. So kind of summarizing these calculations, as your head increases, you can expect your flow to increase, but they're not going to increase at the same rate. Per example, we increased our head by 42%, but our flow only increased by 24%. And then as orifice size increases, the flow also increases, and these kind of increase at a similar rate. So in our example, our orifice rate increased by 33%, and our flow increased by 32%. Well, is there any questions on orifices? Otherwise, I'm going to move on to weirs here. All right, I assume the silence means no questions. So we're going to kind of move into weir flow. So a weir is a notch of regular form through which water flows. So it can be a depression in the side of a tank, a reservoir, a channel, or an overflow dam. Your crest, so the weir of the crest is the edge on which the water flows over. Pre-discharge, just like in orifice, is when the water is flowing over the weir and is discharging into the air. And then a submerged discharge, again, same as orifice, is when the water is flowing over the weir into water. So this is a picture of a broad-crested weir. A broad-crested weir has a horizontal crest on it that's long enough to support the nape of the water. So if this is my normal water body, when it comes over the weir, it's going to kind of come down, you know, so it comes down to a different elevation. This is called the nape, and then the crest is the area that's going to be able to support it. So you're going to kind of see this in a broad-crested weir. You'll see it and like earthen embankments a lot of times. So you're going to have an area that the water is going to flow over that's flat. A sharp-crested weir has a sharp corner or edge, and so the water kind of springs over it. So if you notice the difference between the broad-crested and the sharp-crested here is I have a point here, and the water just free flows over it, and there's nothing supporting the nape on the backside of it once it comes over. This is used for flow measurements. You'll see sharp-crested weirs in the top of inlet structure as well. So here's kind of my basic weir formula. where Q is going to be my discharge in CFS. C is going to be my weir coefficient. L is going to be the length of my weir. And then H is going to be my measured head. So if this is kind of a side view and I have a cutout in a structure, say, my length of my weir is going to be the length of my cutout between the two of them. Whereas my height or my head is going to be from the bottom of the weir to wherever the water surface elevation is. So it's going to vary throughout a storm event. If you're in a situation like up here, where you're with a manhole, your length is going to be the entire length of the manhole. And then, again, I kind of mentioned this a little bit with the orifice. So if you're in a manhole situation, it'll be considered a weir when you're below half the diameter. If it's circular, it'll be weir flow. But if you're above that, it'll be orifice flow. So you can have in a manhole, you can have both weir flow and orifice flow depending on what your head elevation is. So you're going to see weir flows in smaller head elevations. And so part of the question is, where do you measure head at on a weir? So if you look here at the top of my weir, if I come over to here, and this is, I have an elevation here, but if I trace that back left, well, my head is a little bit different at this location. Yep.
Kyle, change your slide.
Oh, sorry, is it delayed?
All right, there we go. Now start there.
Okay. So again, if this is my weir and I take my head elevation at this location and I kind of trace this straight left, notice that my head here is a little slightly different than it is here. So you want to measure your head further enough away that it's not going to have, the weir's not having an impact on it. So typically that's 4H, but if you're like in a pond situation, you're going to kind of go off where your normal water elevation is. So there's a separate equation if you're in a submerged weir. And so the first thing you're going to do is you'll calculate out the free flow, which is that equation that I just mentioned previously, that's CLH to the 3/2. And then you also have to determine what the upstream and downstream elevations of the weir.
Change your slide. There you go.
Okay. So your free flow is going to be, so to figure out your submerged, it's going to be your free flow elevation or flow, which is again that CLH to the 3/2. And then you're going to figure out your upstream and downstream your elevations. So on this picture, I got a weir here, and I'm going to figure out my upstream flow is going to be this H1, and then downstream is going to be my H2. And then notice that they're farther enough away from the weir that the weir's not having an impact on the elevations. So there's common weir flow coefficients. For horizontal sharp-crested weirs, we use a 3.33 weir coefficient. When we have broad-crested weirs, we're going to use a 3.1. There's many variables that can be used, values. These can be found in King's Handbooks of Hydraulics. And then down below, you'll see typical values that like a program like HECRAS would use for weir coefficients, and kind of notice that we tend to use the upper end of the range. Here's a table that shows various broad-crested weir coefficients. And so it's listed as breadth of the crest of the weir in feet. So what the breadth of the crest is we have our crest here, that's this here. And then our breadth is just going to be the length of it, is basically all it's saying. So a lot of times you'll just see this as breadth of the weir instead of written out like that. And the thing to kind of note as well on here is if I have a 4-foot breadth, that as my head changes, my values are going to change as well. So you want to kind of try to get your head as close as possible, but realize that if you have a storm event and you're designing for it to be 3 feet of head, that it might change throughout the storm event. So you might not have the same value. All right. So again, I'm going to kind of go through this first problem and then I'll have one for you guys to work on. So here I have a 30-inch riser. The top of it is going to be at 99. My weir coefficient is going to be 3.1. And I'm going to solve it for water elevations at 199. So this is my general equation again, except for instead of having C here, I already replaced it with my weir coefficient of 3.1. And then I have to kind of find the circumference of my circle, which is going to be pi times the diameter. So again, I have to divide my diameter out by 12 to get to feet. So I'm going to end up with pi times 2.5. And when I solve for that, I'm going to have a length of 7.85 feet. So my head is going to be, I'm at elevation 100 with the water surface, and I'm going to subtract it down to 99 for the top of the weir, and so I'm going to end up with 1 foot of head. And now I have all my unknowns, so I know I found out L and I found out H, so I'm going to plug those into my equation and solve through. And I'm going to end up with 24.3 CFS. So for the second time, again, the circumference is going to be the same, and so L is going to be the same.
Kyle,
Yep.
I have a question. Can
Yep.
you explain to me why this is not an orifice? I know you did it the first, but.
So it becomes orifice flow when so here I have a 30-inch riser. When it becomes half, when this head is half or greater, that's orifice flow. If it's under half of that 30, it's less. So in this case, if this is 15 inches or less, I'm in weir flow. And if I'm above 15 inches, I'm in orifice flow. So if I go back kind of on my problems here, and this one, this head is 1 foot. So I'm in weir flow. And then, and this next one, I'm in half or 6 inches or half a foot. So I'm still in weir flow. So if I get above that 15-inch mark, that's when it turns into orifice flow.
All right, thank you.
Yep. So my head here again is going to be this 0.5 feet. And then so I figured out my L and my H. And so I just plug those into my equation and I come up with a Q of 8.6 CFS. So again, as my head goes down, so does my flow. All right, and so I'm going to have you guys kind of work through this one. This time we have a square riser. And so because I have, if you notice here, I have the top of it's extended back a little bit further. So my water's only going to be able to flow over the 3 sides, the 6-foot side, the 2-foot side, and the 6-foot side. And so you're going to kind of calculate out your L and your H, and C is given at 3.1. So if you want to calculate it out when our water elevation is at 199.5. And then put your answers in the chat so I know if you're kind of getting done there.
Kyle?
Yep.
I have a follow-up question to Mike Isaacson's question is we could simply run weir flow and orifice flow and the lower flow is our controlling factor, correct?
We'll talk about that a little bit later.
Okay.
When we get to kind of combine it into the tube inlet part,
Okay.
the drop inlet structures.
All right, thanks.
Kyle, we have a question from, can you do a 3/2 function in Excel? Do you want to answer that?
A 3/2 function. I guess I'm not sure what you mean by that.
On your equation there, h
Oh.
h to the 3/2. How do you do that in Excel?
Sure there's a way. I guess I don't know. I think maybe you put in exponential. I'm not sure on that one. I guess.
Yeah, there's, yeah, somebody answered it in the chat. If you look there, that's the, you put that under the number of h afterwards. Matt also explained with the power function, you could put 1.5 instead of the parentheses 3/2. And so either way will work.
All right, I'm going to start going through these. So to start off, I'm going to have my general equation here. And the first thing I'm going to try to find out is perimeter of the riser. So I'm going to take my 6 feet plus my 6 feet plus my 2 feet and come up with a length of 14 feet. And then I'm going to calculate my head. So again, we know that the top of the structure here is at 99. And then my water surface elevation is at 100. So I'm going to take 100 minus 99 to get 1 foot of head. And I was given C. So now I know my L, my H, and C. So I plug those into my equation. And I come up with 43.4 CFS. So when I change my head, again, I'm going to calculate out my perimeter, which is going to be that 6 plus 2 plus 6 again. I'm going to come up with 14 feet. And this time, my head's been reduced by half a foot, so I'm going to be 99.5 minus 99 to come up with half a foot of head. And I'm going to multiply that through. So I'm going to have my 3.1 was given, my 14 and 0.5 I enter in, multiply that out, and I come with 15.3 CFS. So again, notice as my my head decreased, so did my flows. All right, and then here's kind of another problem.
Kyle,
yep.
Kyle, on this one, how do you know when you're an orifice flow? Is it when you're have a head above 1 foot because of the 2 foot width length? Yeah,
there's not a hard and fast way of finding that out, but yeah, generally if you're under a foot, you're kind of in that weir flow. It gets kind of a little bit more complicated on these, but yeah, that's a good kind of a good rule of thumb. If you're under a foot, typically on these, you're in weir flow.
Thank you.
Okay, so that's what I'm going to go through an example where we're in submerged flow. So in this case, We have gabion basket with a weir coefficient of 3.1. Our weir length, so our weir in and out of the page is 10 feet. And then we're going to have an upstream head of 2 feet and downstream of 0.9 feet. So first I'm going to solve it for free flow. There's no tailwater, and then I'm going to kind of bring it together and solve for submerged. And then here's kind of our two equations. So I'm going to solve for free flow, and I was given my weir coefficient of 3.1. I have a length of 10 feet, and then my head is 2 feet, as shown in the picture. So I take those, I plug them into my equation, and I come up with 88 CFS. And so now that I calculated my 88 CFS, I have my free flow. I know H1 is 2 feet and H2 is 0.9 feet. And so now I have all the variables in my equation. So I'm able to just plug those in. And I'm going to come up with 77 CFS. So to kind of summarize how weirs work, as head increases, flow increases, but they do not increase at the same rate. So per our example, we increase our head by 50%, but our flow ended up increasing by 65%. So as you change your head in a weir, you're going to have a greater impact than you would in, say, an orifice. And then as weir length increased, flow increased, and they increased at similar lengths. So I increased my weir length by 56%. My flow also increased by 56%. Do you have any questions on weirs?
Kyle, we have a question. Can the weir flow orifice flow condition that Kyle explained be written out in the summary for the group? I guess it's that rule of thumb when you're in weir flow and orifice flow. In that,
correct. Yeah.
I think you had a slide at the beginning.
Yep. So if you're half of the head, basically, or half the diameter, you're kind of in that weir flow, and then once you get higher, you're in orifice flow.
I'm going to put something in the chat, or Matt, can you put that in the chat, what you sent me? That's a really good reference.
I can do that.
All right, so I'm going to move on to pipe flow then.
Kyle, I'm back on the weir.
Yep.
One more question on the weirs. If you could go back to the slide on the weirs. When you have a free flow weir, that is upstream control on a flow direction. But when you have a submerged weir, that's a downstream control, meaning the water backs up into your weir, and that's why you have a reduced flow. Is that correct?
Correct. Yes, yes, it will back up into there a little bit, but it kind of reduced it because what it's doing is it's reducing the velocity, and so as your velocity gets reduced, so does your flow. So it's kind of the same thing. I mean, it does in result back up into the upstream of that.
Mike, I don't have the ability to add that. Won't let me.
Okay, I'll do that. I've downloaded it, so I'll get that in there. And I think that will answer your question, Mark. It'll be a nice little thing. Janet actually makes a comment. We need to check both orifice and weirs to see which one controls. And so what she is saying, when you're in that mixed area, is to kind of do both equations. Is that correct, Janet?
Yes, Mike, that is correct. That applies mostly on anything non-circular. I think Kyle's rule about the 1/2 diameter is usually accurate, but that hard and fast rule, like he said, does not apply to when you come to something non-circular. So yeah, it's best just to check. It's easy to check both. It doesn't take much time.
And Janet, which one would When you check both and you have two answers, which one do you go with then?
Sure, right. So as Doug said earlier, you go with the lower one, of course, as the controlling one. And then Kyle, I think probably later on, you're going to mention, you know, when you have a drop riser, you have a high orifice and a low orifice, the low one being the outlet pipe, and then the high one being the riser itself. I presume you'll talk about that later when you talk about drop structures, so.
Yeah, a little bit. I'm not going to get into that part of it too much. So,
Yeah. So I mean, in general, for the drop structures, you got to check weir flow, high orifice, which is the riser dimensions, and then the low orifice, which is the outlet pipe. And oftentimes it's the low orifice or the outlet pipe that ends up controlling, but we can talk about that later when you get to drop structures. So.
all right. So kind of moving on here to pipe flow. It's kind of the closed conduit of water flowing flow. The area of flow is fixed by the cross section of the conduit. So the water surface is not exposed to the atmosphere, and the internal pressures of the pipe can be equal to, less than, or greater than atmospheric pressure. So if I kind of show, I got pictures down here in the bottom right is going to be the pipe flow where it's completely full, and then on the left is going to not be it because the pipe's not going to be full, so it's going to be open to atmospheric pressure. So some definitions, turbulent flow are when individual particles of water flow in an unpredictable paths in irregular flow. Laminar flow.
Now we have a question.
Yep.
We have a question, and it goes back to the weirs. Does the NRCS underground outlet spreadsheet switch between orifice and weir flow?
So I'll be kind of going over the pond one, yes, but yes, it calculates out both of them. I'm not sure about.
Okay, so that answer will be forthcoming. Very good.
Yep.
Sorry for interrupting here.
And so, where was it? Laminar flow is when individual particles move in parallel layers. So here you kind of see I got a clear tube where the water's moving from left to right in it, and then inside they inserted another tube that's discharging water at the same rate with a red dye on it. And you notice initially when it comes out of this tube through the section, it's kind of a nice parallel line. So that's going to be laminar flow. And then it kind of starts going all over the place. That's turbulent flow. And it's kind of unpredictable. So Manning's equation can be used in pipe flow when you have laminar flow. V is going to be your velocity in feet per second. N is going to be your Manning's roughness coefficient. R is your hydraulic radius, which is your cross-sectional area over your wetted perimeter. And S is your slope. So here's kind of a table of common Manning's ends. And so as you change your pipe type, you'll notice that the ends change as well. And so a lot of these have ranges on them. And sometimes you'll, for example, you could get like a PVC pipe, and we first put it in the ground, it might be one end value, and then over time it might change to another one. So sometimes it's hard to pinpoint an exact Manning's value. For these drop inlets, we're going to kind of be discussing, or we're going to have this flow equation. So this is what's going to be used for culverts and short pipelines. We use this because we're going to have turbulent flow. It's most valid during a free discharge, and this is Bernoulli's equation. And so kind of the bottom of our equation here is going to be taking losses into account. And so I'm going to kind of talk about losses, then I'll come back to this equation. So there's going to be two types of losses, major and minor losses. Friction loss is what a major loss is. And so this is the loss of energy resulting from turbulence between the water and the conduit itself. So the magnitude of the friction loss varies with the pipe diameter and the flow rate. Generally speaking, as flow rate goes up, turbulence goes up, losses will go up. And so our other type of losses are minor losses. And so this is anything that is going to increase or change the turbulence of the water. So we include minor losses when it accounts for 5% or more of the head loss. And so that's going to be more on your shorter pipelines. If you have a long pipeline, your friction losses are going to be a lot greater, so you can usually ignore your minor losses. So there's multiple types of minor losses. The first being an entrance loss. This is going to vary depending on your type of inlet. The less turbulent the inlet, the lower the losses. Then you're going to have enlargement or contraction losses. So this is kind of the same thing, but opposite. One is you're going from a bigger pipe to a smaller pipe, and the other you're going from a smaller pipe to a larger pipe. So as they change pipe sizes, you're going to have a change in your turbulence. So you're going to lose some energy there. Another type is obstruction loss. So, I mean, technically this could be if you had like a rock in your pipe, but when we're talking about it from the design point, we're talking about if you have like a valve, there's going to be some sort of losses with your valve, even if it's open. Continue on here to minor losses. There's going to be bend losses. So anytime you put a bend in your pipe, you're going to have some losses. And then exit losses. So when your pipes or your water's leaving your pipe, you're going to have some exit losses. And so these are constant. So it's a value of 1 when the velocity drops to 0, so the energy drops to 0. So when you're in a submerged discharge, your water's going to be coming out and it's going to hit the a pool of water, and then the velocity of the water leaving is going to drop to 0 instantaneously. And so you're going to use an exit loss of 1. In a free discharge, it's going to be coming out of the pipe and there's going to be no change in velocity because nothing's going to be restricting as it comes out. So the value is going to be 0. So kind of coming back to our general pipe equation, Q is going to be our discharge in CFS. A is going to be the area of your pipe. H is going to be your head difference. So in a case like this, because we're doing free discharge, is going to be from here to the top of your water elevation on the upstream. G is going to be your gravity again, which is going to be 32.2. KE is going to be your entrance loss coefficient. KB is going to be your bend loss coefficient. So if you have a straight pipe, it's going to be 0. KP is your friction loss, and L is your length of pipe. So KE and KP values can be found on pages 385 of the Engineering Field Handbook. And I'll have those tables in the next couple of slides. And then KP is going to vary with N, which again is Manning's N, and pipe diameter. So it's going to change with the pipe type and the pipe diameter. Pages 371 and 372 of the Engineering Handbook have tables that have these already pre-calculated, but you can calculate it using this equation. And then kind of the other thing to note is when I was talking about those losses, those minor losses, we went through a number of them, but in our equation, we only talk about entrance losses and bend losses. And it's just kind of a general thing that, you know, most of the time we're considering these pipelines not to have change in pipe sizes or anything, but if you would put that in, you should add those in. And then again, this is for a free discharge, so you're not going to have exit losses. So common entrance loss values are going to vary with what kind of entrance type you have. So if I'm up here and I'm looking at my concrete pipes, I have a projecting from fill with a socket end and a square end. I have one with a head wall with a socket end, a square end, and a rounded end. I have mitered to conform to fill, and I have an end section conforming to fill. So some examples of what those look like. An end section conforming to fill is going to be your pipe, and then you're going to have your end wall. So this is going to be kind of your manufactured end wall that you can kind of just buy, and it's, you know, one size fits all. If it's a mitered to fill, this is where they're physically going to come back and they're going to cut the pipe to kind of fit the fill section. Projecting is just where you're sticking, your pipe is just sticking out of the end and there's no end wall or anything on it. And then your head walls where here we're going to have this kind of this concrete part above it with your wing wall sticking out. And then when they talked about groove end or square ends, you notice here when these come from the manufacturer, they'll have grooves put in them so they can connect to it one another. And so that's what a groove end is. And if the contractor would have came in here and cut this off and made a nice smooth end, that's going to be your square end. And so sometimes, especially when you're designing, it's kind of hard to know whether or not that'll actually happen. So you just got to do your best sometimes to try to figure that out. And then here's some tables that show you some losses for your bends and some other types of inlet types. So like your hooded inlet is an example, as well as all your different bends that you might encounter. And then they give you your K values. And so I kind of mentioned that those KP values, there was that equation that you can calc out for everything, or there's this table in the engineering handbook that you can come up here and you can find your Manning's roughness, and then you can find your pipe diameter, and you can figure out what your KP is so you don't have to go through all the calculations. And then this is just the continuation of this with Manning values greater, higher Manning values. All right. So again, example, I'm going to kind of go through the first one here. So what's the flow through this pipe when the upstream water elevation is at 200 and when it's at 180? We have a 24-inch pipe with an entrance loss of 1 and a Manning's coefficient of 0.01. So the first thing I'm going to do is I'm going to calculate out my friction loss. So I know N is 0.01 and I know my diameter is 24 inches. And so I'm going to calculate that out. And I'm going to come up with an answer of 0.007. And so here's my general equation again. I'm going to calculate out area, which is pi r squared. And then, so I'm going to have a 2-foot diameter, so 1-foot radius pipe. So notice, big thing to note here is your KP is in inches. Your area is going to be in feet squared. So kind of look out for that. Calculate out my area. So now I know that, and I'm going to calculate out my head. So I'm at 200 feet, and my outlet's at 170 feet. So I'm going to have 30-foot difference. And again, I know KE was given to me. I don't have any bends, so that's going to be 0. My length is 120 feet. That's given to me. And so now I have all my variables, and I'm able to plug them into my equation, and I solve for 81.9 CFS. So again, for when my elevation turns to 180 feet upstream, again, my KP is going to be exactly the same. I'm going to calculate my area using the same methods. And then my head's going to be 180 minus my 170 to get to 10 feet. And so these are all my givens again. Here's my general equation. And I'm going to go ahead and plug those in. And I'm going to come down to 47.3 CFS. And so again, as my head decreases, my flow decreases. All right, so I'm going to give you guys some time to kind of work through this problem. It's pretty similar to the one I just worked on here, except for our pipe size is going to be 48 inches. And again, I'm going to have an entrance loss of 1, Manning's N of 0.01, and we're going to solve for elevations of 200 and 180. All right, I'm going to go ahead and start walking through this. So the first thing I need to calculate out here is my friction loss. And so here's my equation. And I was given that Manning's N was 0.01. I have a diameter of 48 inches. I calculate that out, and I'm going to come up with 0.003. So kind of note that as my pipe diameter went up, my friction loss value is going down. And then here's kind of my general equation. So I'm going to go ahead and I'm going to solve for my area. And so I'm going to come up with pi times 2 squared and get an area of 12.6 feet. And my head's going to be 200 minus this 170. I'm going to have a head of 30 feet. Here's all my givens. And so now I know all my unknowns in this. I'm going to plug them into the equation. And I'm going to come up with 360.5 CFS. So no surprise, but as the pipe went up, so did the flow. So again, as I change my head, all the stuff, the KP is going to stay the same and my area is going to change the same. This time my head's been reduced down to 180 feet. So 180 minus 70 or 170 gives me 10 feet of head. And then I got all my givens up here. So I have all my unknowns in my equations. I'm able to plug those into my equation. And I come up with 208.1 CFS. Again, as my head went down, so did my flow. So kind of to summarize all that, as my head goes up, my flow goes up. But they do not increase at the same rate. So in this case, my head was increased by 66%. My flow was increased by only 43%. And then as pipe area increased, flow increased, but they don't increase at the same rate because as the pipe area increased, my pipe friction decreased. So the larger and the longer the pipe, the greater the increase in flow. Do you have any questions on pipe flow?
Kyle, I'm not seeing any questions.
Okay. All right, so now we're going to kind of combine all those and we're going to talk about drop inlets. So typically there's two types of drop inlets you're going to see. One's going to be here with your manhole and you're going to have a pipe coming out. So this pipe will be your pipe flow section. And then as we kind of discussed, depending on what your water elevation is above the weir is going to be kind of your weir or orifice flow elevations. These also work as if you have a grate and then a pipe's just sticking out and then you put a bend in it. They'll work kind of the same way as they will with this. And so typically we're going to kind of see four types of flows coming out of a drop inlet structure. And we talked about three of them: the weir flow, the orifice flow, and the pipe flow. So if you're out in the field ever and you see one of these structures, you can tell if it's in weir flow. If you can see, if you're standing above it and you see water coming through it and you can physically see the grate. So you're going to have this air vortex that's going to kind of come down. If you get that and you're seeing above that, you know you're in weir flow. So if you're out in the field and you're trying to figure that out and you couldn't see the grate, so you knew you're not in weir flow, you're in one of these three other flows. And so what the next step would probably be to do is look at your pipe and see if your pipe is coming out full. And if it is, then you'd be considered in pipe flow. And if so, if you're not, don't have a full pipe and you're not in weir flow, you're either in orifice flow or short tube control. These are really hard to decipher between the two of them. Even in field tests, they have a hard time because basically the difference between the two of them is an orifice flow, you're going to have this air pocket here, whereas in the short tube, you're not. And what happens, the water gets so turbulent, they can't tell if a lot of times if the air is just from the turbulence or if it's because it is shifted over to the short tube control. And the short tube control, didn't really go through it, but if we were to calculate it, it's the same equation as the orifice flow. And so that's where we're kind of talk about how these structures actually work. So this is just kind of a graph of a general structure and how they found that it worked out in the field. And so if we look here at the bottom, we're going to have flow. And at the side, we're going to have elevations, and they're going to vary. So this row of elevations is going to be the top. So at 0 is going to be the top of my manhole. And then this was going to be what it drops down to. So until it drops down to the kind of the inlet and the upstream side. And then down here is going to be that the downstream discharge elevation. So there, in this particular case, there's 20 feet from the top of the weir to the discharge on the backside. And so if you look at this, we have kind of 4 different lines. We got orifice, short tube, pipe, and weir flow. And if you notice that half of them are dashed and half of them are solid. So why it's the dashed part is that you can physically calculate it using your equations, but in reality, it's never going to happen. So when we're talking about weir and orifice at the beginning, what's going to happen is it's dashed in this beginning is because, as we kind of talked, that it has to get to a certain height before that orifice will start to flow. And prior to that, it's going to be in weir flow. So in this first part, until my head gets high enough, I'm always going to be in weir flow. I'll never be in orifice flow. When I'm in short tube flow, it's kind of the same principle of I can calculate it, but until I get enough flow for my weir, in this case, I can't be in a short tube. And it's the same thing with the pipe. I can't get enough flow to this point to ever be in pipe flow. And then once I get past here in weir flow, that pipe will, because we'd be in pipe flow, that water will back up into the pipe, and it won't allow that air vortex that we kind of talked about on the previous slide to enter into there. So it can't be in weir flow after that point. So we're kind of dealing with this upper section. And this is kind of where these structures get a little confusing. So if I'm at a head here of this line where I'm 4, 8, and 24. So if this is my head, I would have an orifice flow of 2 CFS, a short tube of about 3 CFS, and my pipe flow about 5 CFS. So, convention is going to kind of tell you, well, the orifice is going to control, it's at 2 CFS, so that's going to be the controlling factor. I'm going to have 2. Where in reality, when they've actually done field tests on these, that doesn't hold true. And so in the end of the day, when you have 4 feet of head here, you might get any of these flows. And so that kind of begs the question of, well, where do we use these structures then? Because it's hard when you don't actually know what the flow is to design for it. And so what they kind of say is the best time to use it is when you're in weir flow. So what's going to happen is this part of the curve to this point always holds true. And so what your goal is when you design these is to get it to go from weir flow right to pipe flow and just kind of be able to ignore the short tube and the orifice flow altogether. So what are some situations that you're going to use that for? When you're going to be in weir flow, you're going to have a low head. In our agency, we're going to deal with that a lot. And if you're in like a wetland situation where your water is able to spread out over a long distance instead of going up high quickly. So you'll see those in wetlands to keep this weir flow. And then I kind of pulled this pipe up. So I traced this and pulled it up. And this is where you can get closer to having this pipe flow. So like in this case, I'd be like half a CFS difference, which isn't the end of the world. But what that means is that I don't have this huge head between the top of my weir and coming out the backside of my pipe. And then so obviously is if I shrink this pipe, make this pipe smaller, it's going to shift this curve further to the left and get that. So ideally, when you're designing one of these, it's going to come into weir flow and then it's going to be in pipe flow. And that's it. And you're able to kind of eliminate the orifice and short tube. If you're in a situation where it just works out and you're up here and you're in orifice flow, what they recommend to do is you're going to design the upstream for the orifice flow. So if you have a ponding area, you're going to design it that you're only discharging 2 CFS at a time. But your downstream, you want to kind of equate it for the pipe flow. So if you had like a riprap pad on the backside of your pipe, you want to design it like you have 5 CFS. So you kind of have to be able to do both calculations, and you can kind of ignore the short tube because it's in between the two of them. So kind of moving on here a little bit. So this is our spreadsheet, our pond spreadsheet, and this is for our pipe inlets. I'm not going to go over all of this, but you enter in all your information in blue, and then it's going to spit out a value or a discharge at you, and you're going to kind of live with it. But what really is happening in the background is the spreadsheet's calculating the weir flow, the orifice, the high and low orifice, and the full pipe flow. And then it's going to kind of spit out whatever the lowest of those four is and say, well, that's what your capacity is. So another type that we're kind of going to use in wetland settings a lot is these inline water control structures. So again, that's the same principle. You got your spillway up here. So this can be weir or orifice, and then you got your pipe. So this is all the same, except for now you kind of introduce another pipe in the equation, but that's not really going to affect this portion of the calculations. And I'm going to kind of go through what you're going to kind of see on these. So the first one is going to be the inline pipe controls. So basically this pipe's going to control your flow coming in. Typically you only are really going to see this when your water surface elevation is below the top of your weir or manhole, or there is an option you can put a cover on top of this, and so water won't go into it. So the next type is if you're in weir flow and it says water's over the top. So you know you're in weir flow, your water's over the top of the manhole. So as long as you're fine with that, you should be good. A couple of things to note: if you're in weir flow and you need a greater capacity or want to try to lower the water level or whatever, that, okay, I got to increase my weir size to adjust that. The other thing that I like to kind of do is if you're in weir flow and you're happy with your calculations, is kind of go and play with this outlet pipe a little bit, just to make sure. Maybe you have a 36-inch pipe, and if you reduce it down to 24-inch, you're still in weir flow. So that way maybe you can double check to see if your pipe size is sized correctly. Then you kind of come out with your outlet pipe controls. So that's this pipe controls. And so again, if you need to kind of adjust your anything with your design, you know that your outlet pipe is what's controlling everything. And so this would be need to be increased. And again, it tells you that water's going over the top of your inlet. And again, I like to kind of play with this just to make sure that I don't have this oversized as well. And then kind of the final type is, you know, you're going to get orifice controls. The riser's too low. So it's not that the riser is necessarily too low. It's that you have this capacity. And as we kind of discussed on that previous slide, when you're in these situations, you don't really want to be in orifice control. You'd much rather be in weir control or outlet control. If you kind of get to this orifice control, there's some additional calculations you kind of got to do off to the side if you really want to stay within that. And so I just kind of have an example here of, I have a site that if I needed 1 foot of freeboard in a 50-year storm event, and my model shows that my water elevation comes up to 103.4, but my top of berm is at 104. You know, my model kind of shows that my inlet structure passes 50 CFS and my pipe passes 100 CFS. What can be done? So because my pipe would be controlling, I would try to increase my weir size here to get a larger flow. If I was trying to get it closer to, we talked about, it's kind of an equal ratio of if I increase my weir length, that's going to increase my flow through my weir. So if I would try to double this and try to get it to 100 CFS, I would think I would double my weir. But what happens is as you increase your weir length, your elevation is going to start dropping in your pipe because your flow is going to go up. And as your flow goes up, your head's going to go down because your elevation is going to drop. And so your flow is going to adjust. So granted, we showed on the models that if you increase your weir length, it's going to go up. Well, these are a little more dynamic where your head is also going to adjust as you go through it. That's quite a bit. So do we have any questions on that?
I don't see any questions.
Okay, so the last thing we're going to kind of talk about is buoyancy and flotation. So as I kind of mentioned, a lot of times these structures, we're going to use them in wetlands. So we got to worry about whether these things are going to kind of float up and rip the pipe out, and we got to make sure that they're heavy enough that they stay in the bottom even when they're kind of submerged in water. And so kind of the general principles that the handbook is going to talk about is a body submerged in fluid is buoyant to the force equal. So basically, if your weight's equal to your buoyant force, it's going to kind of be suspended in the water. It won't sink all the way to the bottom, but it won't float all the way to the top. And if your buoyant force is greater than the weight of the object, it's going to float. And if your weight of your object is greater than your force of your water acting upwards, it's going to sink. So we're going to talk about buoyant force. So this is the force pushing upward on an object when you're in water. So I'm assuming most of us have probably been in a pool at one type of our life. And so as you kind of get into a pool, you notice that you're lighter, and that's because the buoyant force is pushing upwards on your body. So this is the equation for buoyant force, where FB is buoyant force. V is your volume of water displaced. And then this is going to be your unit weight of water. So your volume of water displaced in something like this is going to be, you're going to take the size of your box. I should say your volume of your box, you would take your length times your width times your height. And the worst case scenario is going to be when your water gets right to the top of it, but is not overflowing into the structure. So you take that whole volume, and then plus in this case, you take your volume of footer, and that's what's going to get your volume of water displaced. And then you just multiply that by 62.4 and you get a buoyant force. So weight is going to be the force acting downward. So in this case, you would take, it's going to be like the volume of the bodies, or like the volume of the concrete, and then you're going to multiply it by the unit weight of the concrete. So maybe you have 150 pounds per cubic foot. So you'd figure out how much concrete you have, and you multiply that through. You know, if you get a pre-manufactured manhole, sometimes they'll list what the weight is, so you wouldn't have to actually do this calculation. And then when we get that all done, we're going to take our weight and we're going to divide it by our buoyant force. And if that's greater than 1, it's going to sink. If that's less than 1, it's going to float. And then we never actually designed this for 1, though. We always kind of designed it for like a 1.5 for safety factors. So here's kind of an example I'm going to go through. So we're going to kind of determine if the structure is going to be safe from flotation. Assume a factor of safety of 1.5, and the concrete is 150 pounds per cubic foot. So the first thing I'm going to do is I'm going to find what the volume of my concrete is. And so I'm going to take my floor, which is going to be 4 feet by 4 feet, and then I have it 6 inches high. So I'm going to multiply that through. I'm going to come up with 8 cubic feet for my floor. And then I'm going to find the volume of my walls. And so I already calculated this bottom 6 inches, so I'm going to be 3.5 feet high. And then I'm going to be 3.5 feet wide here. And then it's 6 inches thick. And then there's 4 sides, so I'll multiply that by 4 sides. And I'm going to get 24.5 feet cubed. And then I'm going to add those two numbers together and come up with 32.5 cubic feet. And then I'm going to take my 32 and I'm going to multiply that by my 150 pounds per cubic foot to come up with 4,875 pounds. So next I'm going to calculate my buoyant force. And so in this case, it's just going to be the volume of water displaced. And again, I'm going to calculate it for when the water fills up and it's to the very top, but hasn't overtopped into my structure yet. And so in this case, I'm going to be 4 feet tall by 4 feet wide and 4 feet in width. And then I'm going to multiply those through. I'm going to get 64 cubic feet. And I'm going to take my 64 cubic feet and I'm going to multiply it by 62.4, which is my unit weight of water. And I'm going to get a buoyant force of 3,994 pounds. So I'm going to double check that to make sure it works in my factor safety. And when I take my 2 divided by each other, I come up with a factor of safety of 1.22. So in this instance, it would not meet our requirements. So what can we do if our structure is going to float or not meet our requirements? There's a couple options. So we can make it a heavier material. So if this was a metal riser, we can change it to a concrete riser that has a denser material. We can attach anchor supports to it. Typically, this is what's going to be done if you have issues with your pipes floating. And we can increase the volume of our dense material. So you could add a footer into our scenario or make the footer even larger. You can make the walls or the bottom thicker. You can make them 8 inches instead of thick. One of the things you could also do is if you're getting a precast manhole structure, what I've seen done is you'll order it with a sump on it. And then when they put the manhole in place, what they'll do is they'll pour that sump in with concrete so it holds it down and weighs it down larger as well. And so that's a viable option too if you're having it pre-manufactured and you're going to have like concrete truck out on site. It's a pretty quick and easy fix. So I'm going to give you guys a few minutes to kind of go through this and think about it. And so how big would the bottom slab of the structure that we just went through need to be to make sure this will not float? So again, we're going to have a factor of safety of 1.5. We're going to assume that when we extend this out, that's just water above our footer. Concrete weight again is going to be 150 pounds, and we're going to only assume that we're going to extend it in 1 foot increments. So basically what we're going to do is we're going to take this 6-inch bottom and we're going to extend them out in even foot increments to figure out how big that portion of it needs to be for this thing not to float. So if you guys want to go ahead and work on that for a few minutes. All right, I'm going to start kind of going through this. So when you're trying to solve this, there's kind of two ways you can solve this. You can do it the mathematical way, or you can kind of do the guess and check way. Either way is fine. Mathematical way is not for everyone, as guess and check is not for everyone either. So I'm going to kind of go through both of them. I'm not going to try to dive too much in the math, so but ultimately what you can do is you know that your factor of safety equals 1.5, and that you're going to get your weight over buoyancy, and you can kind of solve out your equation to get to the factors of your volume of footer. So are your only variables. And so you're going to end up with an equation you're going to get for your volume of footer, and you're going to solve it out, and you're going to come up with your volume of footer of 19.8 feet cubed. And then so you know that your height here is going to be 6 inches. So you can kind of divide that out, and you're going to end up with 39.6 feet squared. And then you can set up another equation, and you can come up with that. That's going to extend out 1.73 feet. And so that you know you're going to need to extend this out 2 feet on each side if you're doing it in even foot increments. So going through it in the guess and check method, this way you're going to kind of calculate out the volume of your concrete first. So again, I'm going to break out my footer here, and then I know I'm going to extend it on 1 foot on each side. So I'm going to end up with 6 by 6, and then it's going to be a half of a foot thick, 6 inches. So I'm going to get this 18 feet cubed for my floor. Then I'm going to try to find out my volume of my walls. So again, I'm going to be 3.5 feet tall. This is going to be 3.5 feet long, and then I'm going to have 6 inches thick times 4 feet or 4 sides, and I'm going to get 24.5. And I'm going to add those two up. I'm going to get 42.5 cubic feet for my volume of concrete. So I'm going to take my volume of my concrete, and I'm going to multiply that by 150 to get 6,375 pounds. Then I'm going to kind of figure out my buoyant force. So first I'm going to kind of ignore this footer part, and I'm just going to multiply my box. So I'm going to have 3.5 feet high this time, and then 4 by 4 gets me 56. And then I'm going to find out my volume of my slab at the bottom, which is going to be that 6 by 6 by half foot for 18. So this is going to be the same volume as my floor over here. I'm going to add those two together and get 74 feet cubed. Then I'm going to take my 74, multiply it by my unit weight of water, which is 62.4. And I'm going to end up with a buoyant force of 4,618 pounds. So I'm going to divide those out, and I'm going to get 1.38. So that doesn't meet my 1.5 standards. So I'm going to go on, and I'm going to increase my foot size to 2 feet. And again, I'm going to start by finding my volume of concrete. So this time I'm going to be 2 feet out on each side. So I'm going to have 8 feet by 8 feet. And then I'm going to be that 6 inches thick. I'm going to come up with 32 feet cubed. I'm going to find the volume of walls, which is going to be the same from the previous. So I'm going to end up with 3.5 feet by 3.5 by 6 inches by 4 sides. Add those two together, I'm going to get 56.5 cubic feet. So my weight of my box, I'm going to multiply my 56.5 by 150 and get 8,475 pounds. So then again, I'm going to find my volume of the box, which hasn't changed from the last one. So I'm going to be 3.5 feet tall by 4 by 4. And then I'm going to find my volume of my slab, which again is the same volume that I found over here. Add those two together, I'm going to get 88 cubic feet. Multiply that by my unit weight of water of 62.4. And then I'm going to divide those out between each other. I'm going to get 1.54, so I know that this meets my requirements. So that's kind of how you go through finding whether or not your box is going to sink, and some of the procedures you might go through if you wanted to add a footer onto this to figure that out. So any questions about that? So I got about 10 minutes left. So if you have any questions about the buoyancy or if anything that we've covered in general, that would be the time to ask.
Kyle, I'm not seeing any questions.
Okay. So for those of you that want PDHs, again, feel free to email me and I'll get a certificate sent out to you. I'll put this PowerPoint in the chat. And then we're going to kind of send the recording over. I think Penny's going to have it at Land+Water to use. And I'm going to try to get it loaded onto our SharePoint as well. So if anybody wants to use those in future references.